Hey geometries! So here's a quick warm-up to remind us of our special right triangles. We have two of them we need to make sure that we keep in the front of our brains. Our first is an isosceles right triangle where I have a ratio of 1 to 1 to square root of 2. And remember that x can be any factor that you multiply or divide by for all triangles. My second special right triangle is a 30, 60, 90 triangle, which I know is half of an equilateral. So because it's half, I know that this short leg is going to be in a 1 to 2 ratio with my hypotenuse, and my long leg is going to be my short leg times the square root of 3. Now we went ahead and proved these using Pythagoras. And we were able to do that because this relationship gave us one less variable to solve for. And this relationship gave us one less variable to solve for, so we can solve for that missing side. Keeping those relationships in the front of our brain, it's easy for us to say, oh, here's a 30, 60, 90 triangle. So my hypotenuse is going to be double my short leg. And my long leg is going to be my short leg times root 3. When I see a isosceles right triangle, I know that this hypotenuse is equal to this short leg times the square root of 2. So I'm going to go ahead and do some equation solving, and then I'm going to do some rationalizing, and then finally some simplifying. And I know that 5 times the square root of 2 is going to be equal to my side length. 5 roots of 2, 5 roots of 2, because it's isosceles, both of these legs are the same. 8 is equal to this x value times the square root of 3 in a 30, 60, 90 triangle. So we'll do some equation solving and then some rationalizing. There's no simplifying to do for this one because we don't have any friendly numbers. So 8 square root of 3 over 3 is going to be equal to this short leg. And then my long leg is going to be double that. Isosceles right triangle. So if this leg is 7, so is this one. And this hypotenuse is 7 square roots of 2. So those ratios that I can get from 1 to 1 to root 2 and 1 to 2 to root 3 make it easier for me to solve for these missing sides. All right, let's take a look at our next problem. We want to solve for the height of the flagpole. So here we go again in math. We seem to love flagpoles. So we'll take a look at what I have. I have this distance here is 19 feet. This is what I'm solving for, my h. But, I don't know what my hypotenuse is. It's not a special right triangle because it's not a 30, 60, 90 or an isosceles right triangle. Instead, I have this 64-degree angle. So I'm wondering, do I have enough information? I'm tempted to say I need more information in order, and a better pen, in order to be able to solve this one. So I think about, okay, if I had what could I solve? So if I had a similar triangle that was a 64-degree angle, then I would know these two triangles are similar. If I had corresponding sides to find a ratio of, then I could set up a proportion and solve. So and that's exactly what we're going to be doing with our ratios and our unit ratios, like what we talked about at the beginning of class. So let's do some practice and write some ratios for the triangles that we know. We're going to start talking about our short leg and long leg and our hypotenuse. So what I want you to do is for triangles A, B, and C, and D above, A, B, C, and D, I want you to write a ratio of their sides. And the two ratios that I want you to write are the short leg to the hypotenuse and the long leg to the hypotenuse. And we're going to do a little activity with them and talk about putting them into what we call unit ratio. All right, so just take a look at triangle A. I know that my short leg to my hypotenuse ratio looks like this, and my long leg to my hypotenuse looks like this. So go ahead and do A, B, and C, pause the video, and come back and check your work with mine. Okay, so I tried to color code them so it'd be easier for you to see. Our two purple ratios here are going to be our 30, 60, 90 triangles. Let me try to draw that a little better. There we go. These two ratios, and if you see, when I simplified the ratios, I ended up, simplified and rationalized, I end up getting the same ratios, 1/2 and √3/2. For my isosceles right triangles, because my side lengths are the same, and then, of course, when I rationalize my denominator, I end up getting √2/2. So the interesting thing is I can see that there's a constant unit ratio between the sides of these right triangles, and they're exactly what I knew existed anyway. I knew the fact the short leg to the hypotenuse had a relationship of 1 to 2. So I knew that the relationship between the short leg and the hypotenuse was a factor of √2. So when we go ahead and we identify patterns, we can go ahead and take these relationships and use our calculator to come up with decimal values. Try that again. To represent these stories. So this decimal value is the unit ratio of this triangle. And we can do this for each of these fractions. Square root of 2 divide by 2. ⅛ we know is a 0.5. √3/2 we know is 0.886, and we have 0.7071. So what the interesting thing is, when I go ahead and I use decimals to represent the unit ratios, I can use them in my triangle solving. Here's a question for you. Are all right triangles with an angle measure of x degrees similar? So let's take a minute and draw what that might mean. If I have a right triangle and another right triangle, I know I have this angle is 90 degrees. If you knew that this was x and this was x, our triangles would have angle similarity. So I'm thinking if you have any constant value, then you can have a similar right triangle. And if you have that similar right triangle, you can use the unit ratios to help you solve for it. And that's what we're going to be talking about today.